Computer. Okay, good. All right. Good evening, everyone. So this is my final project for CS661 Python programming. The title of it is The Weight Behind a Stroke, and the author is me. I was the sole member of the team for this project. So eh, let's begin. So we go to the introduction. Strokes or cerebrovascular accidents occur to 15 million people globally each year. So, out of I think we have how many couple of billion people we have on the world, maybe like 7 or 8 billion. 15 million people um, have a stroke. Um, So a stroke is defined when a blood vessel within the brain is either blocked or ruptured, which can cause temporary or permanent paralysis or death depending on the severity. Strokes, basically you have either maybe like a blood clot or that gets stuck in one of the small vessels in your brain, and blood can't get to that portion of your brain, and that portion of your brain could die. And that could happen just a regular, something like an ischemic stroke. So it's something ischemic stroke is a temporary blockage, or it can be like a total rupture, which blood's not going, now it's not going into your brain, it's surrounding your brain. And depending on the severity of the stroke or the cerebral vascular accident, um, it can leave either temporary or long-lasting damage or paralysis and even death, depending on the severity. There are certain risk factors that medical staff and researchers have identified as increasing the likelihood of these incidences, such as excessive drinking, smoking, high blood pressure, and more. We have, lots of things that can affect the flow of blood, not only within the body, but within the brain, right? Let's say if someone has, a disease that causes too many platelets and I don't know, they bump their head and all the platelets that are trying to fix that small blood vessel, maybe, or, that damage ends up blocking the brain. Maybe a blood clot travels all the way from your leg all the way up to your brain and causes a blockage like that. There's multiple reasons, and there's also factors that can increase likelihood, blood diseases, high blood pressures stated here, things that, external factors, excessive drinking, excessive smoking, you know, um, interactions with harmful chemicals, radiation, the list goes on, cancers, the list, like I said, goes on. The analysis that this study currently focuses on is that of between body mass index, so BMI, and stroke events, using machine learning algorithms to make predictions between BMI groups and the occurrence of these events. So we can go to the hypothesis. So a little background for is the current study strictly focuses on BMI values and how they correlate to stroke events. As discussed before, there are many studies that focus on correlation between other morbidities, but few that focus specifically on BMI and stroke event occurrence. So we are only focusing strictly on BMI and strokes, not the other comorbidities that may affect stroke, such as, high blood pressure, high blood sugar, diabetes, cardiovascular diseases. They're not focusing on that, just on BMI. In one such case, which Struzzulo et al., 2010 study, they used basic statistical analysis to show correlation between BMI and stroke events. However, they did not use machine learning to come up with predictions based on their findings. In their research, they did find that there was some correlation between BMI and stroke events. But this study that I'm currently doing is trying to basically see how truthful that is, and if we can use machine learning to kind of prove and that to prove that yes, as BMI goes up or down or what have you, we see a certain effect towards stroke events, and we can then make predictions on how much that may affect, how much BMI may affect a given person's risk of having a stroke. So if a patient has a BMI value that is classified as overweight or obese, then we expect prediction models to predict a higher occurrence of stroke events for those patients. This is the hypothesis. So dataset overview. So the stroke prediction dataset is a record of surveyed patients on certain key health factors and stroke events occurrences. I think there was like these that included around 11 different categories. Some of these categories included gender, age, various diseases, smoking status, marital status, residential living, or like if they live in an urban residence, suburban, rural, and the occurrence of a stroke event for that given patient. So this information was gathered from over 5,000 patients' electronic health records, and these patients and the study itself was based in the data set itself was based in Bangladesh in 2020. So the data set in particular is scrubbed of any clearly identifiable patient data that may be used to link a patient to their health information. So of course, if we want to go and if this is a written paper, so they have to adhere to that of the what is it, the ethical review board or ethical research board. So and none of the data that I've used has anyone's personal names or any um, identifiable private information that can be used to link any one given, let's say, patient um, patient factors into any particular patient. It's all scrubbed. So this is the prediction data set, just very basic like EDA, exploratory data analysis. We have the mean age of everyone is around 50. Standard deviation of the age is 17. Have some glucose level information, but we're not really focusing on that. The BMI, we have a range of around 30, and we'll go further into that. And stroke occurrence and identifiable factors or gender, such as if the patient identifies as either female, male, or other. And we also have just a quick heat map of all of the correlation of everyone inside that group or all BMI groups. I'm going to go into more of that in a second. But basically, as we can see here, in regards to stroke and BMI, it's a 0.0012 um, correlation. Very, very slight correlation, honestly. Nothing too big, but again, this is the correlation of all the patients and their given BMIs and the entire overview. And again, we'll go into the specific BMI groups as we continue. So the stroke prediction data set statistics, data has been normalized for missing nominal values by replacing null or non-conforming values with mean for each column. Data has also been truncated to focus on BMI values, stroke event occurrence, and gender. And the study focuses primarily on stroke event occurrences in relation to patients' BMI, separated by classified BMI groups. So these classified BMI groups, BMI values are usually subjected to groups of certain weight ranges dependent on the specific BMI values, right? So BMI groups may vary. A person may have a high BMI, but not necessarily be unhealthy. And due to BMI groups being very before adulthood, patients under the age of 18 were excluded from the featured engineered data set. So before running the further analysis or, all the analysis that I'm currently doing, I removed or dropped everyone that had an age of 18 and below from the entire data set. So these classified BMI groups are BMIs of less than 18.5, which would suggest underweight, between 18.5 and 24.9, which is a healthy weight range, 25 and 29.9, which may indicate overweightness, and over 30 is usually an indication for obesity. So exploratory data analysis on the underweight group. This is a correlation heat map of the underweight group. The underweight BMI shows negligible correlation between being underweight and stroke event occurrence. As we see here, it's 0.011, which is very close to what we saw in the overview heat map, which was 0.012, if I remember. And the correlation may be skewed because amount of patients that fall within the subset of underweight. So there's not a lot of patients that are underweight within the data set. So it could be skewed these lower numbers because not enough data. Okay, so now we're at the density of the BMIs within the underweight group. So 30% of the patients in the underweight group have a BMI value of around 17. On the lower end, the BMI values are between 10 to 12, meaning like extreme malnourishment. So those individual adults that have 10 or 12, we're looking at, again, just extreme malnourishment. Maybe some of these patients could be like 70, 80 pounds if they're, 5'7", 5'8". It would put them within that group. Overall BMI values in the underweight group have slight variance, where one-third of all patients in the group would be classified as slightly underweight. And I'm not sure if I mentioned this before, but BMI is the body mass index, and it's just a calculation that relates a person's height to their weight. And it gets you get a certain value from that. And that value is then corresponds to a individual's like weight group. So we have a violin plot now of the underweight BMIs versus the stroke events. So only one patient in the underweight BMI category had a stroke event, where most patients in the underweight category did not have a stroke. Doesn't necessarily mean patients are healthy. We're only looking at stroke event occurrences. So as discussed before, BMIs vary. BMI isn't the whole story of a patient, but we're just looking at this one specific category to see if there is any correlations or anything that we can use prediction modeling for to kind of come up with a conclusion or results or analysis on BMIs and strokes. So this is the regression modeling for underweight BMIs. So I did two types of regression modeling, the linear regression and logistic regression. As you see on the left, it's a linear regression model image. So the linear regression model leaves much to be desired. It's only a slight increase of stroke occurrences within the BMI range, with coefficients being 0.002, rounded off to 0.003. Very, 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 very slight. And an intercept of negative 0.013, which is not really anything to write home about. Logistic regression models show as BMI goes up, the chance of stroke goes up as well. With the, logistic models using log odds, with the coefficient log odds being 0.049. So around, log odds of like not necessarily 5%, but, if you do the log odds using that coefficient, you would get you would get that particular number. The number varies between BMIs, right? And the intercept being negative 4.13. Again, it's a very weird, not weird, but um, the intercept starts off as negative, but then again, there's only so many people that have, let's say, BMIs that are, 11 or 10 or 9 or 8. So I assume as even though the intercept is so negative, as the real indicator, that coefficient value will indicate again a slight chance of stroke for as the BMI values within this class go up, this BMI group goes up. So now we have the healthy weight group. So the healthy weight group heat map shows a negligible correlation with only 0.002%, which was lower than our correlation of the weight group before, which was 0.011. According to, actually, it's a little bit more, sorry. So yeah, I think it's a little bit more, but still negligible in the grand scheme of things. And according to the heat map, identifying as actually a female has a higher correlation of suffering a stroke event than even BMI. So it's one of those indications that was just like, huh, it's pretty interesting, right? 0.057 rounded off, 0.006 correlation to 0.002. That's 4 thousandths of a point. Still, grand scheme of things, pretty negligible, but something to keep an eye out for, especially when involving heat maps. Okay, so the density of the BMIs in the healthy weight group. Healthy weight group shows more variance between BMI values than what we saw in the unhealthy weight group, where around 25% of patients, or the density of the patients in the healthy weight group, skew within the 24 BMI range. A violin plot now of the healthy weight BMI versus stroke event. So we see here that patients that measure a BMI value of around 24 have the highest probability of stroke event occurrences, but this can also be because of the density of patients within the group being around 24. So, not necessarily telling us much, just that, if patients that have 24 BMI, may have a higher chance of stroke, but that could also be because there is such a, a great number of patients that are within that 24 BMI value range. The median between both groups lies between the 23 BMI range. And then in the non-stroke event group, the lower half of outliers extends almost to the bottom of the plot. So if we look at the no event, which is identified as the zero point 0, we're using binary values here, where 0.0 is no event and 1.0 is an event. 0.0 event is it's no occurrence. So we have some regression modeling here. So again, model shows a slight increase of stroke occurrence in our linear regression models, 0.0026. And our logistic regression model shows as BMI goes up, the chance of stroke does go up again, very marginal, 0.0059, 0.006. But again, it's something to keep track of because as we continue, we saw this in the underweight group, but we also saw this with the healthy group, that as their BMIs go up, the log odds also go up. So now we have the overweight group, the EDA. So the heat map of the overweight BMI shows correlations of only around like 0.011, which is slightly higher than the previous two weight groups, and a strong correlation that BMI has to any of the other core categories within the map is age. So before we saw gender, which is female, and now we see age, and age is at 0.044. Okay, so the overweight group has the most evenly distributed density between the individual BMI ranges so far, and actually within all groups, as we'll see. And the BMI values between 26 and 30 relatively plateau at a density of around 20% or zero point 0.2 density of all people within the group are between the ranges of 26 and 30 BMI. Patients that this violin plot. Patients that measure a BMI value of 27 have the highest probability of a stroke event occurrence. Patients in the non-stroke group have an even distribution of BMIs between ranges, and the median of both the stroke and non-stroke groups hover between 27 and 28, with more patients having a higher probability of strokes in past when past a value of 30. Regression modeling now. Our linear regression model shows a slightly greater increase of stroke occurrences as BMI increases, with coefficients of 0.0026. And our logistic regression model shows similarly as the log odds go up. And actually, this goes up quite significantly, in my opinion, with 0.077. That is, in the grand scheme of things, right? That's pretty significant. As your BMI goes up, a 0.077 log odds, depending on what BMIs that you're going up from. If you do the analysis of those, you do the log odds of that, you can get the definite number. But 0.077 log odds is a pretty measurable number. So now we're at the obese group. So the correlation heat map of the obese weight group is, we have a negative correlation of stroke events actually at negative 0.03. Very surprising. Wasn't really expecting this. I was expecting I want this group actually to be the highest, but the data doesn't lie. It shows here that it is definitely a negative correlation, which is the first within the previous three groups that we've seen. A negative correlation, again, it's not really unexpected. I mean, it is really unexpected, but based on the observations that we've seen in the previous groups. But we have to remember that BMI does not specifically correlate with health. A bodybuilder can be classified as obese. And would you call a bodybuilder obese? Well, medically they are, but maybe social culturally, we wouldn't call them obese. They're just, have a lot of muscles. Okay, so the density of BMIs in the obese weight group, it really skews towards the 30-40 BMI value range. The highest density for this group is with patients who have a BMI value of around 32, with a few outliers who may have a BMI value that goes past 70. And we have the violin plot, so of obese weight and BMI versus stroke event. So again, as expected, an almost equal variance between BMIs within both the stroke and non-stroke groups, as we've seen with healthy weight, with those BMI values being within 24. For the obese group, it's BMI values within the range of 32. And this also may be the reason for the negative correlation as seen in the heat map. As you see in the non-stroke plot, we have BMI ranges that go past 70, 80, 90 for the at least the probability, right? Based on what a violin plots, right? Plots probability in regards to X and Y axis. So, maybe those who were in the extreme levels of within the BMI range, right? Those 70s and stuff may be actually skewing the the non-stroke events. So our regression modeling for obese weights, BMIs. So we have a linear regression model that shows again, a decrease of stroke occurrence as BMI increases, which is very contradictory data that I've seen here. Again, with the logistic regression models, also shows log odds of negative 0.022. So according to our regression models, as we gain weight in the obese weight class, or weight group, then we have a lower chance of having a stroke, which, it seems odd, but at the same time, there's certain outliers. As we can see here, I have some patients that are 80 or 90, have a BMI of 80 or 90. But yeah, it could be because those patients, they just haven't had have a stroke yet, because I would assume, if an obese person has a stroke, or one we can say is conventionally obese in social cultural terms, then that would be pretty detrimental, right, towards their well-being, as all strokes do. But again, so the results. Results. For the most part, there is a minimal increase of stroke event occurrences as BMI increases. though obese groups show negative correlation, right? So we used the prediction models, we used our data analysis, exploratory data analysis skills, and and statistics to actually see how for each groups um, how BMI affects the occurrence of a stroke. Regression models also show support for an increased outcome of a stroke event as BMI increases. So within the four groups, three of the groups, the underweight, healthy, and overweight, have shown increases towards a stroke event occurring as BMI goes up, right? And we saw those with not only the linear regression models, but also the logistic regression models. And though not necessarily significant enough for all groups, right? Especially with the obese group, because the obese group itself, kind of maybe it was skewed, who knows, right? The group showing especially, yeah, so the obese group was showed contradictory results to that of the overweight group. So of the groups that we expect, we saw, the jump between the obese group and the overweight group, the obese group showing a high log odds for a stroke event as opposed to the obese group that showed a negative log odds. And conclusion. So conclusion is, a patient who has a BMI that is classified as overweight may have a slight higher occurrence of stroke events, though for patients who identify as obese, more data is necessary to support such claims. So, just in general, we can see that BMI does have some effect on how a person, the occurrence of a stroke event on a given person. But we had contradictory data in regards to our obese data set where it showed negative. So it doesn't really support our initial hypothesis as well as, we expected it to. But for three out of the four BMI groups as discussed, um, our hypothesis stands kind of that, as using our prediction models where the prediction models show that as BMI goes up, at least to a certain extent, we'll say, right? So once you go past the underweight to overweight groups, underweight, healthy weight, overweight, then as your BMI goes up, your your occurrence of stroke events also goes up. And the obese category, we showed a negative correlation, but there's a lot of things that may have factors into that. Um, and we need to obviously there needs to be more exploration in that. And thank you. If any questions, comments, concerns, please feel free to email me. Here's a list of all my references, and have a good one.